All right, in this video, I'm going to talk about the residuals. We also call error or deviations, okay? So look at this, residuals. What are the residuals? For a fixed values of x, the distance of the point from the line, the best fit line, is called residuals, okay? You see that? The d1 is one residual because this is the estimated line y equals to a plus bx. Those dots are the real data, right? So the distance of the data from that line is called residuals. Some people also call error, or some people also call the deviations. Okay, we denote this the sample residual by E sub I, where E sub I is yi minus yi hat. Yi is the data, observed data point, and yi hat is the value that you estimated from y equals to a plus bx, okay? Where yi denote the observed sample values and yi hat is the estimated values using the regression equation, all right? So what is the residual plot? If we plot x along x-axis and E sub I along the y-axis, okay? That is if you plot x versus the residuals or the error, that is called the residual plot. So this kind of plot is particularly useful when you test the normality, when you test the homogeneity of variance, all those kind of things, right? That's why we handle with the residuals, not the individual data usually. The population parameter for E sub I, this E sub I is the distance between the observed sample data minus the estimated line, the value at the estimated line, right? But if it is in the population, we denote by epsilon. We call epsilon sub I, okay? So outliers and influential points. Outlier is a point that is farther away from other points. Influential points are those that affect the graph of the regression line, which means without those points, the regression line is far better, goes through most of those points. Okay, let us see a random example of x and y, and then I'll show you how do I find out the error or the residuals, and how do I plot the residuals, okay? So I have two data x and y. So x is circumference of something and height is the circumference of those things. So when the circumference is 1.8, height is 21. When x is 1.9, height is 33.5, y is 33.5, 1.8 again 24.6. There are two data that has same x values, right? And 2.5, 40.7 and so on. So first of all, to find out the residual plots, what you need to do is you need to find out the regression line the way that we did before, okay? Exactly the same way we do that. So whenever you do that, then you find out that the regression line is y equals to 13.9505 plus 7.1909x. That's what you find out, okay? That's the line of regression. That is the I would say sample regression line, okay? Now, if you want to find out the error, okay, or let's say this way. So if you plot x and y as a scatter plot, this is what you get. This is the scatter plot. You see that? This is the scatter plot. Just all these blue dots are the scatter plot. But if you find the line and plot the line, this is that you get. This is the line you get, okay? This the black line is the line y equals to 13.9505 plus 7.1909. All right, guys. Now, what is the error? So, for example, here error is, you see that distance between that red dot minus that one, okay? Also distance between that minus that one. Distance between this red dot minus that one. That are the errors. So, how do I find out that? Is first of all, you need to find out the values of the line at those x values, meaning the predicted value. For this x value, what is the predicted value? For this x value, what is the predicted value? For this the y value. Because this is the real value, real data. Okay, and these will be the predicted. This will imply the predicted value. That means plug in x equals to 1.8, 1.9, 1.8 and so on. That's what you will get. Okay, guys. All right, let's see that. This is the x value, circumference. This is the y value, that is the height. Predicted value will be you plug in 1.8 in x, 1.9 in x, and whatever you get is the predicted value. Now, what is the residuals? Residual is the the original value or the data minus the predicted value. 21 minus 26.89, that is negative 5 point. 33.5 minus 27 will be 5 point, and so on. These are the residuals. Okay, you see that whenever you plot the real data in the scatter plot and you plot the line, this is what it looks like. But whenever you plot x values versus the residual, this is what it looks like. Okay, so what you can say from here is, if the data points are scattered along this horizontal line or along this line, then you can say that roughly you can say that the data is linear. You see that? If the data are randomly scattered from this line, like many data are above or many data below and less data above or below, like that, like distributed in not a good proportion, right? Then it is non-linear. If the residuals are curved like this or like this below or above that horizontal line, then you can also say that the distribution may not be the relationship may not be linear. Okay, also what you can see here is, you see that, so if the data are more scattered on one side of this line and like one end of this line, and the less scattered on this one end of this line, you can see here, you see that the more data are close to this line, right? You see that more data are close to this horizontal line, and some data are very far away, right from this line. You see that those are far away, the residuals are far away. So basically the scatter plot and the residuals shows almost the same thing. Okay, but just the way how it shows is different. Here you look at around that slanted line, whatever line you get, but here you find out, you look at around that horizontal line that goes through 0. Okay, because the average of the residuals is always 0, that's why you get that average line, or this line stands for that y equals to a plus bx line. Okay, so it is around 0. That is the mean, that is the average of those residuals. Okay, this is the line. If the dots are close to that residual, that 0, okay, residual line, I would say the average of the residuals, then you see that the relation is linear. Look at this example. What we can see here is, from residual plot we can better see whether the data are around the horizontal line or not. If the data are approximately equally distributed above and below the horizontal line, then the linear regression model is a good model. Okay, let us look at this. Pair the scatter plot and the corresponding residual plot in the above graph. You see that? See, these are the scatter plot, these are the residual plot. So you need to pair. Is a scatter plot match this scatter plot is same? I mean, this the residual plot A is that the same for is this residual plot A is for scatter plot I or double I or triple I or IV, like that. Okay, what do you think? You see that in the scatter plot I, you see that on the left the dots are very close to the line, but whenever you go to the right, the dots are more scattered. Also, all the dots are close to that line, meaning that it is linear. Okay, but whenever you go to the right side, then you will see more scatteredness, more spread of the dots, right? So which one do you think? I think like you see that on A, everywhere the scatteredness or the spread is almost the same, and it is linear close to the line, but spread is a little bigger there, right? You see that almost the same everywhere on the left hand and right hand. On the B, you see that it is a curve type, it is not linear. You see that on C it is linear, close to the line everywhere, but it is the spread is same everywhere, right? But in the D, on the left there is a less spread, on the right there is a more spread. So scatter plot I match with D. You see that? Now scatter plot double I, let's talk about that. It is spread more, I mean the spread is same almost everywhere, but you see that the spread is more than IV. You see that the spread is more than IV. Okay, so this one must, the double I must be A, because it is linear close to the line everywhere, and spread is same everywhere, but it is more scattered, right? This double I belongs to A. Similarly, scatter plot triple I belongs to B. Why? Because it is not linear. You see that? On the left end and right end, all the dots are below. In the middle, all the dots are above. You see that the similar behavior in the residual plot. And IV is for C. Why? Because it is linear. All the points are close to the scatter plot, or close to the line, right? And then the spread is better. I mean, spread is less than the scatter plot double I. So here, C has scatter, the spread is less than plot A, right? That's why this is the C is the residual plots for IV, B is the residual plots for triple I, and D is the residual plots of I, and then A is the residual plots of double I, okay? And the prediction interval, look at this, we discussed that already, right? Prediction interval already in one example there. So for any values of x, we use the regression line y hat equals to a plus bx to predict y values. We can also predict the intervals for each of the predicted y value. You see that? So one of the y value will be given by the data, but you find out the straight line, you find out the prediction line, or you say the best fit line or the regression line. You find out the regression line using the x and y data. After you find out the regression line, you can predict y value for any x value that is not in the data. But if you are curious about what will be the prediction interval for each of those y values, then the formula to do by hand is this, okay? The following formula is used to find out 1 minus alpha percent prediction interval for a given x sub 0, okay? Y hat minus margin of error is less than y hat plus margin of error, where margin of error is given by t alpha. So you use the t table, okay? Alpha 2 tail table, and n minus 2 degrees of freedom, SE, and root under 1 plus 1 over n plus this value, right? And SE is given by that value, is the measure of variation of the residuals. Note that we use n minus 2 degrees of freedom to find out t alpha half value. N is the number of pairs, x sub 0 is the given value of x, and x bar is the average of x that is used on this formula, right? And y hat equals to a plus bx0. Usually we use software to find out the prediction interval for each of the x value. See lab 10 for the example. So we did that already, right? You see that I did the prediction interval here, okay? This will be the prediction interval on line 174. You do predict. First of all, you need the y equals to a plus bx line, okay? Let me write down that prediction interval. Okay, so what we do, first of all, you find out the y equals to a plus bx using that formula, right? That's what we used before. That's what we got. Oops. And then so that's what we had. Now to find out prediction interval, I did so y value comma x value, that is the data dot frame we denote by a, right? And you do predict. Model 1 is that where you got y value and x, a value and b value, and then a and the interval is prediction, okay? So whenever you do that, that's what you get. Okay, guys, so this is the prediction interval that we found. Okay, so the next thing what we are doing here is we want to test hypothesis for the regression coefficient. What is the regression coefficient? That is b or beta. In the population we denote by beta, in the sample we denote by b, right? Because y equals to a plus bx. So y equals to, we denoted by y hat equals to a plus bx is the sample regression line. And so we do uppercase y equals to alpha plus beta times uppercase x. This is the regression line for the population, right? This is for sample. So we want to test, so far we found out the equation of the regression line in the population and sample, right? So here, this is the regression coefficient of population. This is the regression coefficient for the sample. So regression coefficient for population and regression coefficient for sample. So what we want to do next is we want to test the hypothesis for the regression coefficient beta for the population using the b value from sample. Okay, that's what we are going to do next. All right, So first of all, let us talk about the assumptions. So what are the assumptions that is required for the hypothesis testing? Okay, for the regression coefficient. So number one is linearity. Linearity means the data must be linearly distributed. So X data and Y data must be linearly distributed. The data in residual plot should be distributed nicely around the horizontal line. You see that? Linearly distributed. Linearly distributed. It is linearly distributed because they are along the line, but you see the spread is not the same. So we call that the variance is higher here on this end and variance is lower here. Here the variance is equal everywhere almost. Here the variance is equal almost everywhere. This is not linear. These three are the linear. This is not linear. So that's what the residual plots test the linearity. Okay, that's what it says. The scatter plot must be linearly distributed. The data must be linearly distributed. The data in residual plots should be distributed nicely around the horizontal line. Okay, that's the assumption number one. Number two, the constant error variance. What does that mean? That means the variance of the data for each x values must be almost equal, meaning this is called the homoscedasticity. In residual plot, the data should be equally scattered around the horizontal line. More serious methods such as Goldfeld-1 test or Pagan test can be used. To solve this problem, we can take log of the variable. So what does that mean? That means in the residual plots, the data, the error must be equally distributed, or the spread of the error must be same everywhere along the horizontal line. Okay, that is the same variance of the residuals. That's what it is saying. Okay, so if you find, look at this. So here, same variance in the error plot everywhere. Same variance in the error plot everywhere. This is not linear, no need to talk about that. Okay, and here, this is linear but not the same variance everywhere. Okay, so this is the graphical way to test if the variance are equal or not. Okay, if the homoscedasticity is satisfied or not. Okay, if this is violated, you can transform the data and then do the log transformation or do other things. Okay, you see that? You take the log on the variables. That's what you can do. Next is the normality of the errors. So for each x values in the residual plot, the y values must be normally distributed. So we can detect it by plotting the histogram or residual plots, residual QQ plot. Okay, so you can do the histogram of the residual or you can do the QQ plot of the residual to test the normality. So solution, if it is not normal, if you found that the normality is violated, you can you can transfer the data into the log. And no multi-collinearity. That means in case of the multiple correlation, the x variable must be independent to each other. Okay, so meaning that if there are more than one independent variable like x1, x2, x3 and one y variable, in that case x1 and x2, x2 and x3, all of them must be independent. So you can detect it by running correlation between x variables. Okay, so basically the residual plots does almost all of these three, these two. Basically residual plot do these two of those assumptions. Normality I will show you how to do that. Okay, normality also we will be doing for the residuals, and no multicollinearity in case of the multiple correlation. That's what we will be discussing later. We'll have to test if there is a correlation between the independent variable. Okay guys, so I will show you how to do the hypothesis testing of the correlation coefficient in case of the simple correlation, hypothesis testing for the regression coefficient in case of the simple linear regression, and in case of the multiple linear regression in the next video. Okay guys, thank you.